Variation of parameters in section 4.6, that's on page 187. We talk about first what's known as the Wronskian, capital W for Wronskian. So given a set of solutions, or a list of solutions, the Wronskian would be listing the first and taking a derivative, listing the second and taking a derivative, and finding the determinant, which is the product of those minus the product of those. And there it is. Now, this is going to generalize for more than two solutions later on. So generalize for as many solutions as you have, which is why I'm giving you this formula in the form it is. In our book, they have it in terms of y sub 1 and y sub 2 only. I'm talking about this. Here I have it in terms of y sub m because this worked for third order, fourth order, fifth order, as high of an order as you like to go. Consider y double prime. Again, the key in our definitions versus the author, we like the one right there. So make sure that's a 1, and that's how you read P, Q, and G if needed. If P, Q, and G are continuous on an open interval, and y sub 1 and y sub 2 form a fundamental set of the complementary solutions. So these are the solutions of the complementary, remember, homogeneous part. Then the particular solution would be the series, and in our case, it's going to be just in this section, it's going to be, so we plug in 1, y sub 1, the integral from t naught to t of g of s, and Wronskian of 1 divided by the Wronskian evaluated at s, plus y sub 2, the integral from t naught to t, g of s, Wronskian evaluated at 2, well, not evaluated at 2, Wronskian sub 2, I'll tell you what that means in a minute. So in this case, that's all there is. Now I'm going to give you this formula on the test. That formula right there, I will provide on the exam. So you don't have to memorize it, you just have to use it. Where the Wronskian evaluated at sub m is simply replacing the mth column, in this case since it's a 2 by 2. So Wronskian sub 1 is 0, 1, replacing the first column by 0, 1. And that will be y sub 2 prime. And Wronskian sub 2 will be y sub 1, its derivative, and 0, 1. Again, the reason I'm giving you all of this, because this is going to generalize for any dimension of the solutions, or any order, I should say. So let's apply it and see how that works. I'm going to get that formula right next to me, and I'm going to use it. I'm going to shrink it up. Oops, that didn't work. Okay, let's see it again. Let me copy it. And here we go. Well, there's the formula again that will be provided on your test physically, so you could see it. On page 191, I believe, we have the following solution. So notice this trick. This is no longer an exponential, sine or cosine specifically, or a polynomial. If it's anything other than those three, then you have to use other method. This is one of them. Variation of parameters is one of them. But what it requires you, so y equal the complementary plus the particular. You need to find the complementary and use it in the particular. So the complementary, you know the trick by now, e to the rt, r squared plus 1 equals 0. So r equal plus or minus I. So we know we have a cosine of t, and it doesn't matter which one you call y1, y2, it makes no difference. You're going to get the same answer anyways. So I know the complementary now is c sub 1. Let's say cosine of t is y sub 1, but you do have to name them and be consistent as you do this. So there's my y. Now I need to find the particular solution. And to find the particular solution, I'm going to need, let me see. I need it a bit thinner. I had one, but I can't find it now. There. So the particular solution here is going to equal, and let me fill in the blanks. Let I equal 1, you're going to get y sub 1, the integral from t naught to t. And I forgot to say that I mentioned that t naught is arbitrary. It could be anything. Yeah, this t naught right here is arbitrary. That's just a constant. So we ignore it when we plug it in. We just want the general. G of s, in this case, it's going to be secant of s W sub 1, I'll get to that in a minute, divided by the Wronskian ds plus let I equal 2, so you get y sub 2, the integral from t naught to t, secant of s, the Wronskian sub 2 divided by the Wronskian ds. And that's pretty much how it works. Well, let's work out a few of those. Meaning, first of all, what's the Wronskian? The Wronskian is really the solutions. I'm going to go by cosine of t and sine of t. You list them out if you have only two. Take a derivative, and the Wronskian is the determinant of this. Cosine times cosine is cosine squared of t minus a negative sine squared of t. Well, this is the magic identity. That's a 1. So this denominator is a 1. So the particular solution is really y sub 1, we're calling that cosine, just be consistent. The integral from t naught to t, the denominator is 1. The second solution is the sine. That's a 1. Let's figure out, so there's a secant of s, and there's a secant of s. That doesn't change. What we're going to work on right now is what's W sub 1. W sub 1 is replacing the first column by 0, 1 and listing that solution. So that was, and if you ever forgot, just take a derivative. Sine of t, cosine of t. So what is that? That is 0 minus sine of t. But I'm going to evaluate it at s ds. And the second is going to be the cosine of t, negative sine of t. And I'm going to replace the second column by 0, 1. That's going to be 1 minus, so that's just cosine of t. S. Because it's evaluated at s ds. So, now that I have those, I'm looking at the particular solution being the cosine of t times the integral from t naught to t. That is going to be, isn't that 1 over cosine? So that's negative sine, so that's a minus. Sine over cosine, that's tangent of t. Tangent of s. Plus the sine of t times the integral from t naught to t. And this is going to be, cosine over cosine is just 1. So the particular solution would be negative the cosine of t times. Isn't that, what was it? Natural log of the secant of x? I should say s. Evaluated from t naught to t. And this is going to be just s evaluated from t naught to t. Now we ignore the constant. So when you plug this in, you get natural log of secant of t minus some constant, we ignore that, plus the sine of t times t minus some constant, we ignore that, and we say the solution to this problem, the entire solution, is going to be c sub 1 the cosine of t plus c sub 2 the sine of t minus the cosine of t natural log of secant of t. Of course, you could say negative natural log of cosine of t if you wish, whatever makes you happy, plus t the sine of t. And notice we find the solution of the particular including coefficients. So there it is, just a formula to get used to. Again, this is going to come back when we do higher order. We're not there yet. Okay, we get to the second problem. We're going to do the same thing. So, you know how it's going to go. There it is. Let's put it right there and use it again. So let's find all of these things first. First, I need the solutions for the homogeneous so I could figure out the rest. So let's do that. So first we have e to the rt times r squared plus 2r plus 1 equals 0. So we have e to the rt can never equal 0. Hopefully that's getting old. We have r equal -1. So we have e to the negative t and t e to the negative t to be a solution. So first things first, y equal c sub 1 e to the negative t plus t e to the negative t plus 1. Yep, that will be the homogeneous. Now the particular, we're going to have to find that. Well, y particular is going to equal, depends on a few things. Let's see. First things first, if we go for the Wronskian by it is, well, we're going to list e to the negative t and t e to the negative t. Derivative of that is negative e to the negative t. Here we're going to use the product rule, 1 times e to the negative t minus t e to the negative t. So when we find this, that will be the product of those, e to the negative 2t minus t e to the negative 2t minus, so that becomes a plus, minus a negative is positive, t e to the negative 2t. These cancel out, you're left with e to the negative 2t. Okay, that's the Wronskian. And if I want to find w sub 1, the Wronskian with 1, that will be 0, 1 right there, and we already have it. It's right there, just copy it. T e to the negative t and e to the negative t minus t e to the negative t. And here, w sub 1 will be 0 minus t e to the negative t. Got it. And if you want to find w sub 2, that will be e to the negative t, negative e to the negative t, 0, 1. That will be simply e to the negative t minus 0. Got all the pieces that we need. The particular is going to be, and I'm going to write it out, m equal 1, the integral t naught to t, g of s, that's e to the negative s. W sub 1 is negative s e to the negative s ds divided by Wronskian evaluated at s negative 2s plus y sub 2 times t naught to t. Actually, you know how it goes. We're calling and y sub 2 is really based on what I have is t e to the negative t. And again, e to the negative s, that's not going to change. The Wronskian is not going to change. And when I take w sub 2, we said that was e to the negative s ds. And that finds the particular solutions, including the coefficients. I mean, there's a plus in there. Plus meaning something positive, not a sign. E to the negative t. Now, if I look at this integral really, and aren't those e to the negative 2s? That becomes a negative, and that's simply s ds plus t e to the negative t. And wouldn't these cancel out? You're looking just t naught to t of ds. And wouldn't you say the particular solution is negative e to the negative t times s squared over 2 evaluated from t naught to t plus t e to the negative t times s evaluated from t naught to t? Now again, why did they ignore the constant? Because it gets absorbed, but we don't have to worry about that. They just ignore it all the time. So that will be negative t squared when you plug that in over 2 e to the negative t minus a constant. Let's ignore that. And this is t times t plus t squared e to the negative t. Let me just make sure. Yeah, it seems they're matching. The particular is going to be what in this case? What's negative 1/2 plus 1? Isn't that 1/2? So my final solution would be c sub 1 e to the negative t plus c sub 2 t e to the negative t plus 1/2 t squared e to the negative t. Do you see that this is modified? Everything's taken care of. Now on something like this, I wouldn't have used this trick. On something like this, if I had a choice, I would have used the particular to be a e to the negative t, and I would have went over there and modified it by t and by another t. But here for practice purposes, we want to just make sure that we could do this. And we're going to do the same right there. We're going to apply this trick again. We want to get used to it. Again, it's going to come back when we go for higher order. And it's going to save us a lot of work. Even though it might seem like it's a lot of work right now, well, it wouldn't be on the long run. So again, y is going to equal the complementary. Let's get the complementary out of the way. That is e to the rt times r squared plus 9 equals 0. So r equal plus or minus 3i. We're talking about the cosine of 3t and the sine. Of course, you could put sine first. I'm just used to doing that. C sub 1, the cosine of 3t, plus C sub 2, sine of 3t. That would be the first complementary solution. And based on that, I'm going to pick all the rest. And let me get all the pieces. So the particular solution, I'm going to look at, first I want the Wronskian of this, and that happened to be the cosine of 3t, sine of 3t. And if you're wondering, what if I put sine first? You could, but then everything will alter accordingly and you get the same answer. That's negative 3 the sine of 3t, and that is 3 the cosine of 3t. And the Wronskian will be 3 times the cosine squared of 3t plus 3 times the sine squared of 3t. Factor a 3 out. Cosine squared plus sine squared is a 1. So I got the Wronskian to be 3. W sub 1 is 0, 1 sine of 3t, 3 the cosine of 3t. That is 0 minus 3 the sine of 3t. Got it. And W sub 2 will be the cosine of 3t, negative 3 the sine of 3t. That is 0, 1. That would be, and I know this formula is not in the book because they're talking about 2 dimensions only, or they're talking about second order only. When they get to higher order, they introduce that. I want you to get used to that. And we say the particular solution is, and now let's see how it works. Y sub 1, right? Y sub 1, the integral from t naught to t. The g of s, g in this case is the secant squared of 3s, times w sub 1, which is negative 3, the sine of 3s, evaluated at s, right? And they're using s because, oops, wrong key. They're using s, they're getting us used to what's going to be known as Laplace later on, Laplace transforms. They use s, not a big deal. You could use any variable. The Wronskian was just 3, and that is ds. So since we're doing that, might as well, we know what y1 is. We called y sub 1 the cosine of 3t. And the y2 is going to be the sine of 3t, the integral from t naught to t. Secant squared of 3s, that's not going to change. 3 is not going to change, but w sub 2 is going to be the cosine of 3t. So attached to the t. 3s. Well, let's see if we can clean this up just a bit. So that's going to be the cosine of 3t over 3, the integral. And let's see, 2 naught to t. That negative, oh, this cancel out. So it's just negative. And secant squared, isn't secant squared 1 over cosine squared? And this is cosine. Okay, I don't want to confuse you, but that would be just secant, 1 secant. So this cancels one of those. You're looking at the sine of 3s, the integral from t naught to t of secant of 3s ds. This piece we could get quickly. The second piece we gotta work on just a bit. If I let u equal the cosine of 3s, du will be negative 3 the sine of 3s ds. So this will be negative cosine of 3t. When I replace those, that's the integral from t naught to t. This is going to be u squared, and that's going to be negative 3 du. So that's u to the negative 2. Add 1 to the power. So the integral of u to the negative 2 du. Add 1 to the power divided by that. That's negative 1 over u. And u in our case is cosine. Right? Evaluate from t naught to t. Plus the sine of 3s. And we know this is either negative natural log of cosine, absolute value of cosine of 3s, or secant, whatever you want, depending on which calculus book you used. So this is going to cancel out. That's 1/3, and it's just, oh, I rushed it. That is negative cosine of 3, positive now, when you multiply those, over 3 into 1 over cosine of 3t. When you plug the t in, again, we're going to ignore the t naught, this. Ignore that all throughout the book. And when we plug that in, that's natural log of cosine. So it's sufficient just to plug it in. And my final answer is going to be 1/3 minus sine of 3s, natural log of cosine of 3s. Oh boy, I'm mixing things up now. You gotta forgive me. The outside is y. It doesn't have, it's a t. I just copied an s because of all the s's. Okay, and I didn't do that on the second one, just this one. So the general solution for all of this, if you just want to find the particular solution, there it is. But if you want to find the whole solution, y equal, and was it cosine and sine? I lost track. It was cosine and sine. So the solution is going to be c sub 1, the cosine of 3t, plus c sub 2, the sine of 3t, plus 1/3 minus the sine of 3t natural log of cosine of 3t. Again, we find the solution with the coefficients. That's the deal. Now I want to point to one more thing. Find the general solution. Here they don't specify what to use. It's up to you to use whatever you want, but you do know we don't have a choice. So again, when I say that, I mean when they give me a function other than an exponential, a sine or cosine specifically, or a polynomial, I have no choice. So here we're going to play the game and do this because I want to elaborate on, since I have a choice, what to do in this case. So this is the same problem, except I added something to it. Well, let's see how this works. We know that the complementary y equal the complementary solution plus the particular. Complementary, r squared plus 1 equals 0. So we have r equal plus or minus I. So we have a cosine of t and sine of t. Not bad. We didn't do this problem before, did we? It looks like we did. No, we didn't. Now, why are they all coming up to be sine and cosine? Actually, that turns out to be the application most used. So it's not a coincidence. So far I have y equals c sub 1, the cosine of t, plus c sub 2, the sine of t. All right, now I want the particular solution. In the particular solution, I'm going to find a few things. First, I'm going to find the Wronskian. We know what that is. By now, that's a 1, right? And w sub 1, again, we know what that is. I can go to the previous sections, like that one. It was a sine and cosine, wasn't it? W sub 1 was, what did we get? W sub 1 was negative the sine. What did I just erased it? That's 0, negative sine of t. So negative sine of t and cosine of t. negative sine of t, and you could derive it if you really need. It's not that big a deal, right? Negative sine of t, and w sub 2 is the cosine of t. Again, you could list them, take a derivative, and just play with them. All right, so how does that work? The particular solution is going to be y sub 1, which is the cosine of t, the integral from t naught to t, of g of s, that's tangent squared of s, times w sub 1, which is negative sine of s, divided by 1 ds, plus the sine of t times the integral from t naught to t of tangent squared of s. That doesn't change, the 1 doesn't change, the s doesn't change. Well, the second was a cosine of s. So if I look at the particular solution, it's going to be the cosine of t times the integral from t naught to t of negative tan squared and sine. Well, let's see. Tangent squared is sine over cosine, isn't it? So that is the sine squared of s over cosine squared of s times sine of s ds, plus sine of t times tan squared of s times sine squared of s over cosine squared of s times cosine of s ds. That is negative cosine of t times the integral. This is 1 minus cosine squared of s. So this is going to be t naught to t. So that's going to be 1 divided by cosine. So that's sine of s divided by cosine squared of s. And cosine over cosine is 1 minus sine of s ds. And this is going to be 1 minus cosine squared of s. So we take 1 divided by, I'm writing very clumsy, I should take my time. So this is going to be, oh, this is going to cancel one of those. So 1 over cosine is secant of s, and cosine cancels 1 cosine, and there it is. Okay, now you notice we just did this part. This part here, that u equal cosine du will be negative the sine. So that's negative 1 over u squared. So that is 1 over u, and u would be cosine of s. And here, what do you take a derivative of to get negative sine? The cosine of s. Okay, there you go. T naught to t. And this is, oops, this is natural log of secant of s. Secant of s, I think, plus tan of s, and this is just the sine of s evaluated from t naught to t. So this is going to be negative the cosine of t times 1 over cosine of t plus cosine of t. We're going to ignore the plug it in the constant part, and we do that all the time. Secant of t plus tan of t minus sine of t. Let me just think. Yeah, let's multiply by all of it. So altogether, we're looking at y equal c sub 1 the cosine of t plus c sub 2 the sine of t, which is the complementary part, minus, that's going to give you a 1. That's going to give you a cosine squared of t. That's going to be plus the sine of t times natural log of secant of t plus tan of t minus sine squared of t. Now, when I get to this solution, notice here what they said. They said find the general solution. when I want to find this in general, this I can't use the undetermined coefficients. But I know that that's this. Can't I say I'm going to use superposition, and instead of doing this formula, can't I say y sub p is going to be a e to the 3t, y prime is going to be 3a e to the 3t, y double prime is going to be 9a e to the 3t, again, because I know this is sine and cosine, right? So can't I say now, take y double prime, 9a e to the 3t, plus y, a e to the 3t, and that should equal e to the 3t. That means 10a equal 1, a is 1 over 10. So can't I say the particular here is 1 over 10 e to the 3t, and all what I'll do, I'll copy this right here because I already did that. So I figured this out the long way, but there's no point in using that complex formula if it's a form out of something that I did already, right? So there's no point in me doing it using that formula if it's the undetermined coefficient method. That's very quickly just to tag next to it. Because this I could find quickly. Polynomials, I could do that too. The integration is not really the way to go on those three since I know how to use them. And that's pretty much it for this section.